Hello friends, welcome to my channel. This is Isro question paper, Fluid Mechanics Part 3. An automobile moving at a velocity of 40 km per hour is experiencing a wind resistance of 2 kN. If the automobile is moving at a velocity of 50 km per hour, the power required to overcome the wind resistance is how much? Options are in kilowatt or kilojoule per second. So its coefficient of drag is Fd by half rho a b square. Fd is drag force, rho is density, a is area, v is velocity. So data given are v1 equal to 40 km per hour and drag force, wind resistance, drag force 1 is 2 kN and v2 is 50 km per hour. Fd2 we have to calculate, then power. From Fd2 we will calculate power. So Ft is Cd into half rho a v square. So Ft is proportional to v square. Drag force is proportional to velocity square. So from here Fd1 by v1 square equal to Fd2, drag force at second case, velocity v2 square. So Fd2 is 2 into 50 square by 40 square kilonewton. So from here we will calculate power. Drag force in second case Fd2 is 2 into 50 square by 40 square. This is in kilonewton. So power to overcome that wind resistance is Fd2 into V2. So V2 in kilometer per hour. So we have to convert it to meter per second. 2 into 50 into 50 divided by 40 into 40 to V2 is 50 into 5 by 18. Then to 25. Then here 125 into 25 by 18 to 4, it's 72. So 120, 25, 70. 7, 12 into 25. 300 by 7. So approximately 42 point something equal to, from option 42 point, A is our answer, 43.4 kilowatt. 0.4 kilowatt. Kilowatt or kilojoule per second or kilonewton into meter per second. A constant head water tank has on one of its vertical sides two identical small orifices issuing two horizontal jets in the same vertical plane. The vertical distance between the centers of orifices is 1.5 meter and the jet trajectories intersect at a point 0.5 meter below the lower orifice. What is the approximate height of water level in the tank above the point of intersection of trajectory? First we will draw the diagram. Let this be point 1 and this is point 2. This is the trajectory. Let this distance is x, where the two trajectories intersect. This height is given 0.5 meter. Then this is 1.5 meter. Let it be capital H. Take it as Y3. Here, what is the approximate height of water level in the tank above the point of intersection of trajectory? So H we have to calculate. This H, it's already this is two methods we will apply here. Method 1. In method 1, if you add this 2 here, this distance already will get 2 meter. 1.5 plus 0.5, already 2 meters. So H should greater than 2 meter. From option A is not possible, C also not possible, D also not possible, because it is 2 plus Y3 meters. Y3 value is greater than 0, so B is our answer. This method we can use, or calculation also we can do. Method 2. Method 2. We know CV equal to x by 4yh root over. This formula we will use here. In both cases, CV1 equal to CV2, so x1 by 4y1 and h1 root over equal to x2 by 4y2 h2 root over. x1 and x2 both are same. Horizontal distance, this distance x, both are same. So 4y1 h1 equal to 4y2 h2. Here in case 1, 4 into y1 is 0.5 plus 1.5, it's 2. Then h1 is y3, height above that orifice, 4. Then second case y2 is 0.5, h2 is 1.5 plus y3. So 4 cancel. Then 4y3 equal to 1.5 plus y3. So 3y3 equal to 1.5, y3 equal to 1.5 by 3, it's 15 by 10 into 1 by 3. 1 by 2 is 0.5 meter. They asked 0.5 meter. We have to calculate edge height. We got y3 equal to 0.5 meter. We have to calculate capital H. Capital H equal to y3 plus 1.5 plus 0.5. So 0.5 plus 0.5 plus 1.5, it's 2.5 meter. Same B answer we get. The velocity components in the x and y directions are given. U equal to lambda xyq minus x square y, b equal to xy square minus 3y4 y to the power 4. The value of lambda for a possible flow field involving an incompressible fluid is, lambda value we have to calculate. Fluid is incompressible. So already we discussed, if fluid is incompressible, then divergence of that v vector is equal to 0. Del v equal to del dot v equal to 0. So del by del x I cap, del by del y j cap plus del by del z k cap into dot product. B vector is u is lambda xyq minus x square y I cap plus v is xy square minus 3y4 y to the power 4. This is j cap. So del by del x of lambda, this is 0. This value is 0 for incompressible fluid. xyq minus x square y plus del by del y of xy square minus 3y, sorry, this is 3y4 y to the, this is 4 y to the power 4. So we'll get lambda yq minus 2x y plus equal to 0. Here 2xy minus 3y4 into 4yq equal to 0. 4 cancel. 2xy minus plus 2xy cancel. Lambda yq equal to 3yq. So lambda equal to 3 for incompressible fluid. These two things are important. If the governing equation for a flow field is given by lambda square phi equal to 0 and the velocity is given by Vp equal to delta phi, we know delta square phi, this is Laplace equation. Here it's phi, del square phi by del square phi by equal to 0. This is Laplace equation. and we know phi is velocity potential, and velocity potential exists only for irrotational flow, exists only for irrotational flow. This is also very important. And here, if velocity potential satisfies Laplace equation, means it satisfies continuity equation. And the flow is possible. And one more thing was already discussed. For irrotational flow, curl of V equal to 0 or del cross B equal to 0. So already we got this is velocity potential function exists means flow is irrotational. So curl of V equal to 0 or del cross B equal to 0. So from option A is our answer. Chances of occurrence of cavitation are high if the A. local pressure becomes high, B. local pressure falls below the vapor pressure, Thoma cavitation parameter exceeds a certain limit, D. local temperature becomes low. B is our answer. Local pressure falls below the vapor pressure. The general equation of continuity for three-dimensional flow of an incompressible fluid for steady flow. Continuity equation for incompressible fluid and steady flow. We know general form of continuity equation is del rho by del t plus del by del x rho u plus del by del y rho v plus del by del z u v w equal to 0. This is general form of continuity equation, or we can write this one. Sometime in this term also they are asking. In this term they are asking general form of continuity. In IES so many times they asked this question. In this term, second term, both are same. For steady flow, del rho by del t equal to 0. Then that general form for steady flow, it will become rho v equal to 0. This is also important. We can write this one as plus del z rho w equal to 0. For steady and incompressible fluid, rho is constant. In that case, we will get del by del x of u, del by del y of v plus del by del z of w equal to 0. This is our continuity equation in 3D form. Or we can write this one as del of v equal to 0. Both are important. In this question, they asked this one. So A is our answer for incompressible and steady flow. If general continuity equation they will ask, this is the answer. A liquid compressed in cylinder has a volume of 0.04 meter cube at 50 kg per centimeter square and a volume of 0.039 meter cube at 150 kg per centimeter square. The bulk modulus of liquid is how much? K we know, minus dP by dV by V. From here, initial volume is 0.04 meter cube. Pressure is 50 kg per centimeter square. V2 is 0.039 meter cube. Pressure P2 is 150 kg per centimeter square. So del V equal to 0.04 minus 039. It will come 0.001 and del P equal to 150 minus 50 is 100 kg per centimeter square and V is V1 0.04 meter cube. So K equal to minus del P divided by del V by V. So 100 del V 001 by V 0.4. So 100 into 1 by 10 to the power 3 1000 into its 4 by 100. 100 cancel. K equal to 4 into 10 to the power 3 unit is kg per centimeter square. It's 4000 kg per centimeter square. B is our answer. A fluid jet discharging from a 100 mm diameter orifice has a diameter of 80 mm at its vena contracta. The coefficient of contraction is how much? D1 given 100 mm, D2 equal to 80 mm, coefficient of contraction CC, area of jet at vena contracta divided by area of orifice. Pi by 4 80 square by pi by 4 100 square. 80 by 100 is 0.8 square, 0.64. And we can use another method also. We know CC value is 0.61 to 0.69. So from option A also not possible, B also not possible, C also not possible. D is our answer. Directly we can get 0.64 D. Both method we can use. Next. If a jet of water of area A, capital A, strikes with velocity v, a series of flat plates mounted on a wheel of mean diameter capital D rotating at n rpm, then force exerted will be equal to how much? Force exerted and a series of flat spats, water jet strikes. Fx is to rate of change of linear momentum m v minus u, and u we know pi dn by 60. M is rho a v into v minus u, m dot. This is m dot. Mass flow rate rho a v into v minus pi dn by 60. So rho a v in terms of divided by g, and option in terms of unit weight. So divide g v minus pi dn by 60. Fx, the force exerted per unit weight. So from option B is our answer. The maximum height of a siphon for a liquid of specific gravity rho under atmospheric conditions is, its answer D, 10 by rho meters. A centrifugal pump with peripheral speed V was selected for a total lift of 100 meter. Actually, pump was to be operated for a total lift of 400 meter. The peripheral speed should actually be other conditions remaining same. So centrifugal pump peripheral speed V. We know for pump or centrifugal pump, power, head and discharge with speed, it's NQ n square, it's n square and NQ. In terms of diameter, it's dq d square and d to the power 5. We have to use this one. Head is proportional to n square and head is proportional to d square. D also not required here. So h is proportional to n square. h1 by n1 square equal to h2 by n2 square. V equal to pi dn by 60. So here h is proportional to v square. From here we can get h1 by v1 square equal to h2 by v2 square. We have to calculate peripheral speed in second case. v2 square equal to h1 by h2 into v1 square. So h1 by h2, h1 is 100 meter and 400 meter into v1 square, it's v square. So v2 square 1 by 4 v square. So v2 equal to v by 2. I made one mistake here, so again I am doing here. h1 by v1 square equal to h2 by v2 square. v2 square is h2 by h1 into v1 square. v1 square already given, initial speed is v. So from here we will get v2 equal to 2v. From option A is our answer. The specific speed of pump and turbine respectively are given as specific speed of pump. Ns for pump is Nq h to the power 3 by 4. Specific speed for turbine is n root p h to the power 5 by 4. First pump, then turbine. So this one not possible because first is turbine, then pump. Here, yeah, B is our answer. N root q h to the power 3 by 4, np h to the power 5 by 4. Match list 1 with list 2 and select the correct answer. List 1 forces, list 2 dimensionless groups. This one already discussed. This is very important. All numbers. Viscous force is Reynolds number. Reynolds number is inertia force by viscous force. Then elastic force. Elastic force is for Mach number. This is 4. Then surface tension for Weber number. Then gravity is for Froude number 2. 1432. 1432. C is our answer. Given that alpha 1 equal to nozzle angle, n equal to number of rows of moving blades in a velocity compounded impulse turbine, the optimum blade speed ratio. Optimum blade speed ratio is rho. It's U by V1. So if you calculate this one, we will get rho optimum is cos alpha 1 by 2n. This is for impulse turbine. So from option D is our answer. Thank you friends. Thank you for watching my video. If you like my video, then subscribe it. Thank you.